Now we're just going to look at exact power series expansion for a few more functions to conclude this module. In the previous video we established that e to the x can be seen as the sum of a power series, specifically the sum from 0 to infinity of x to the n over n factorial, and that this equality is true for all x. Similarly, we've established that sine x can also be seen as the sum of a power series centered at 0 for all x, and this power series is a series from 0 to infinity of -1 to the n x to the 2n plus 1 over 2n plus 1 factorial. So you only have the powers of x that are odd powers. Another power series representation that we have seen and used extensively, maybe the most classical one, is the sum of a geometric series, namely representing the function 1 over 1 minus x as the sum of the geometric series of common ratio x, as long as x is in absolute value less than 1, that is, strictly between -1 and 1. So now when we look at the power series representation for sine x, it is not hard to guess that there should be something similar for cosine x. And we can just play the same game and look at the successive derivatives and try to find a formula in order to write out the Maclaurin series for cosine x, and then we'll justify that this Maclaurin series actually converges to the function cosine x for all x. So if our function is cosine x, the derivative of order 0 is the function itself. First order derivative is derivative of cosine, it's negative sine. The second derivative is the opposite of the derivative of sine, so it's negative cosine. The third derivative, I'm differentiating negative cosine, and the derivative of cosine is negative sine, so I get positive sine x. And then the derivative of order 4 is the derivative of sine, which is cosine, and which happens to be also our original function, or derivative of order 0, which means that after that we repeat the same derivatives. Specifically, the fifth derivative is actually the first derivative. The derivative of order 6 is like the second derivative. Derivative of order 7 equals the third derivative. Derivative of order 8 is like the fourth derivative, and so on. So you see that in particular we get plus or minus cosine for the even order of differentiation, 0, 2, 4, 6, 8, and so on. And we get sines, plus or minus sines, for odd order of differentiation, order 1, 3, 5, 7, and so on. And more specifically, we can write out these derivatives of even and odd order. The even numbers are represented by numbers of the form 2n, and you see that the derivative of order 2n is -1 to the n cosine x. Indeed, if n is 0, then we get the function cosine x, and -1 to the 0 is positive 1. So that works. When n is 1, get the second derivative, which is negative cosine x, which matches our -1 to the 1 cosine x. When n is 2, we get the fourth derivative, which is cosine x, and it's -1 to the 2, that's positive 1 cosine x, and so on. And similarly, for the derivative of odd order, we can write odd numbers under the form 2n plus 1, and what we obtain is -1 to the n plus 1 sine x, because in particular when n is 0, we get the first derivative, which is -1 to the 1 sine x. Indeed, it's negative sine x. And then when n is 1, we get the third derivative, which is positive sine x, and that corresponds to -1 squared sine x, and so on. So, because we're looking at the Maclaurin series, we're going to plug x equals 0. That means that for the derivatives of even order, we get -1 to the n times cosine 0, which is 1, while for the derivatives of odd order, we plug x equals 0, we multiply by sine 0, which is 0. So all of the terms of odd order in the Maclaurin series are going to disappear, and what remains in our Maclaurin series for the function is just a series from 0 to infinity of the terms of even order. So they are of the form -1 to the n over 2n factorial x to the 2n. And moreover, because the successive derivatives are plus or minus sine or cosine, they're always in absolute value bounded above by 1 for all x, which means that by Taylor's inequality, we can conclude that the nth remainder is bounded above by 1 times absolute value of x to the n plus 1 divided by n plus 1 factorial, which is the term of a convergent sequence. For each x, this sequence converges to 0 as n goes to infinity, and therefore the remainder goes to 0, which means that the Maclaurin series converges to the function cosine x. We have no condition on x for this to work, and therefore cosine x is exactly the sum of this power series from 0 to infinity of negative 1 to the n x to the 2n divided by 2n factorial. So for sine you only have the terms of odd power, for cosine only the terms of even power. So now we have these four power series representation for standard functions. And we're going to look at one more standard function, namely the natural logarithm of 1 plus x, and we're again going to look at the Maclaurin series. So what happens when x is close to 0? The function is natural log of 1 plus x, so that's a derivative of order 0. The derivative of order 1 is 1 over 1 plus x, which I'm going to write 1 plus x to the power negative 1. Of order 2, I'm differentiating 1 plus x to the negative 1, so I get negative 1 times 1 plus x to the negative 2. When I differentiate again, I get negative 1 times negative 2 times 1 plus x to the negative 3. And then if I differentiate again, negative 1 times negative 2 times negative 3 times 1 plus x to the negative 4. And if we continue this way, you see that we multiply negative 1 by negative 2 and so on up to negative n minus 1. And we multiply by 1 plus x to the negative n. Now this product at the beginning, we have n minus 1 term. Each one of them contains a negative sign, so we can factor out negative 1 to the n minus 1. And what remains is 1, 2, 3, and so on up to n minus 1, which we can write n minus 1 factorial. So we can rewrite this a little more compactly as negative 1 to the n minus 1 times n minus 1 factorial times 1 plus x to the negative n. Now what we're interested in if we're looking at the Maclaurin series is the nth coefficient for our Maclaurin series, which is going to be the nth derivative of f evaluated at 0 divided by n factorial. So at 0, the first term is 0 because it's ln of 1, which is 0. And then if n is greater or equal to 1, and I plug 0 in this formula, I get negative 1 to the n minus 1, n minus 1 factorial, and then a power of 1, which is just 1. That means that our Maclaurin series, when n is 0, we get a coefficient 0, so we can forget about that and start at 1. And when n is 1, the coefficient is negative 1 to the n minus 1 times n minus 1 factorial divided by n factorial. The n minus 1 factorial divided by n factorial leaves me with just an n at the bottom. So we get the series from 1 to infinity of negative 1 to the n minus 1 over n multiplied by x to the n. And now, well, in fact, we didn't really need to calculate all the derivatives in order to establish that ln of 1 plus x is equal to this series, at least when the absolute value of x is strictly less than 1. Because, well, this is a calculation we've made before, the derivative of natural log of 1 plus x is 1 over 1 plus x, which we can write as the sum of the geometric series of first term 1 and common ratio negative x. And so we get the series from 0 to infinity of negative x to the n, which I can write negative 1 to the n, x to the n, and that's valid as long as the absolute value of the common ratio is less than 1, which means absolute value of x less than 1. And that means that f of x is an antiderivative of this power series. We can integrate term by term if we stay on the same interval strictly between negative 1 and 1. So up to some constant, f of x is a series from 0 to infinity of negative 1 to the n times x to the n plus 1 over n plus 1. We can easily calculate the constant by plugging x equals 0. If I plug x equals 0 in the function f, it's ln of 1 plus 0, that's ln of 1, that's 0. And on the other hand, if I plug x equals 0 in this power series representation, I get the constant plus something where all the terms are 0, and therefore c is 0. So c is 0, and I have this series of -1 to the n over n plus 1, x to the n plus 1. You see that we start with n equals 0, which gives me power 1 for x. So we can shift the index and start at 1 instead, and that we get -1 to the n minus 1. We get n at the bottom instead of n plus 1, and we get n for the power of x instead of n plus 1. And this is valid as long as absolute value of x is less than 1. So here we've established that the function ln of 1 plus x is equal to this Maclaurin series of the function for absolute value of x less than 1. Now when we proceed this way, we know that the interval of convergence for the geometric series for f prime is exactly the open interval from -1 to 1, but when we integrate, we don't know if we have the same interval of convergence. We know that we have the same radius of convergence. So it's worth taking a look at what happens at 1 and -1. Well, at -1, there's not much to consider, because if you plug x equal -1 in this series, you see that you get -1 to the n minus 1 multiplied by -1 to the n. That's -1 to the 2n minus 1. In other words, that's -1 to something that is always odd. In other words, we get -1. So that means that at x equal -1, we get the series from 1 to infinity of -1 over n. And that just is divergent, because if it were convergent, it would be, for the value, the opposite of the series of 1 over n, which is a divergent p-series. So it is divergent at -1. What about at 1? Well, that's where the calculations we've done with the successive derivatives will come handy. We have established this formula for the nth derivative of the function, namely that it's -1 to the n minus 1, n minus 1 factorial, 1 plus x to the negative n. That means that at x equal 1, if I look at the nth remainder at 1 using the Taylor-Lagrange theorem, it tells me that this remainder at 1 is the value of the n plus 1's derivative of f at some point c between 0 and 1, divided by n plus 1 factorial, multiplied by x to the n plus 1 in absolute value, but x is 1. So what we obtain here is just -1 to the n over n plus 1, because I'm sorry, it should be -1 to the n over n plus 1 times n plus 1 factorial, multiplied by 1 over 1 plus c to the n plus 1. And because c is greater than 0, 1 over 1 plus c is less than 1, and therefore this 1 over 1 plus c to the n plus 1 goes to 0. So that means that the nth remainder at 1 goes to 0, and we can conclude that ln of 1 plus x is equal to the sum of this Maclaurin series for x strictly greater than -1, but less than or equal to 1. So in particular, we have equality for x equal 1. Now another power series representation that we have established in a previous video using the same sort of argument, namely writing the fact that the derivative of arctangent is 1 over 1 plus x squared, which you can think of as the sum of a geometric series of first term 1 and common ratio -x squared, writing out that the derivative as such a power series representation, and then integrating term by term to obtain a power series representation for arctangent, what we obtain is that arctangent is equal to this series from 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1, and this is with a radius of convergence of 1. We know that it is valid between -1 and 1 if x is strictly between -1 and 1. It turns out that we can include the endpoints, but it actually takes a little bit more time to clarify why this is the case, so we're going to admit this. So here is a list of power series representations for standard function that you should memorize. You should know all these formulas because, as you will see in the next module, they are very handy. So now it is time for you to turn to homework.